Welcome back. Here are the answers to the Build Your Understanding problems. I'm thinking that since these are fairly similar to stuff we've done before, that I don't need to try your patience by talking through them all. So I've just put all the answers up on the screen. You can pause the video as you need to check your answers. For anything you didn't get correct, see if you can fix it, and if not, come to my office hours to get help with anything you missed if you need to, or go to the discussions and go into questions about Chapter 3 and let me know there where you got stuck, and I'll do my best to help you. Next, we'll talk about how to do this type of hypothesis test. The test statistic for this type of parameter will be the chi-square test statistic, which is n-1 s squared over sigma naught squared, where s is the sample standard deviation, sigma naught is the standard deviation that's going to be assumed true or valid in the null hypothesis. N, as usual, is the sample size. And a couple of notes, the chi-square distribution, like the t-distribution, is different for different degrees of freedom. So we need to know the degrees of freedom. And just as with the t-distribution, it's one less than the sample size. And then I'll just mention also that this test does require that the population be normal. Our procedure is exactly the same as for the previous two types of hypothesis tests. It's only the test statistic that's different. So I'm going to launch right into an example without any further discussion of the method. So here's the example. A quality control engineer recalibrates a candy producing machine in order to reduce the variability in the weight of the candy it produces. Right? They want it to be a little more reliable. Before the recalibration, the standard deviation in the weight of the candy it produced was 0.75 grams. After the recalibration, a sample of 11 candies is weighed, and the standard deviation of their weights now was 0.6404. So that's a point estimate of the standard deviation. It is less than the old standard deviation, but this is just a sample of 11 candies. So let's conduct the appropriate test, hypothesis test, at the alpha equals 0.05 level of significance to determine whether the engineer succeeded. And by succeeded, we mean he successfully lowered the standard deviation by recalibrating the machines. Okay, so the null hypothesis is always a statement of equality. So that's going to be the statement that the standard deviation is still at 0.75. The alternate hypothesis, the one the engineer is hoping to support, is that the new standard deviation is actually less than 0.75, that the machine is now more reliable. When your alternate hypothesis is a less than, you're going to be looking for things on the left end of your table. So that's a left-tailed test. The test statistic, because we're doing a hypothesis test about a standard deviation, the test statistic we use is the chi-square. So let's see, chi-square, that's, we're going to do n-1 s squared over the assumed sigma squared. So let's see, our sample size is 11. So 11 minus 1, and notice that's also the number of degrees of freedom. The sample standard deviation was 0.6404. We're squaring that. And then in the null hypothesis, we assume that the standard deviation is 0.75. Okay, so run those through a calculator and you get 0.7291. For the p-value, we need to go to our chi-square table And the chi-square distribution, that's that one that's not symmetric. And it's not centered at 0. 0 is actually on the left there. But we're looking for area to the left of 7.291. Okay, so we're looking for this area. And that's the chi-square distribution with 10 degrees of freedom, one less than the sample size. So we go to our chi-square table with 10 degrees of freedom. So let's see, 10 degrees of freedom, and I'm looking for 7.291, or as close to 7.291 as I can get. So let's see, it looks like probably between these two numbers, the closest one to 7 something is this. So I'm going to use 0.9 as my approximate chi-square value. But remember that the chi-square table, like the t table, gives you area to the right. Okay, so it says here up here to remind you, area to the right of the critical value. Okay, so that 0.9 that I got is for this area. And that's not what I want. I want area to the left. How do I adjust for that? Well, remember the total area under a probability distribution is 1. So 1 minus 0.9 is the other stuff that's to the left, so that's going to be 0.1. So the p-value is approximately 0.10. Then what we do with that is we compare that to the level of significance. 0.1 is greater than 0.05, our level of significance. And so let's see, if the p-value is greater, do we reject or not reject the null hypothesis? We do not reject the null hypothesis when the p-value is, greater. Didn't get the greater in there. What do we conclude? So we've decided not to reject the null hypothesis, but our conclusion has to be stated in terms of H1. So what we're basically going to say is that we can't support H1. We cannot support H1 because we're not rejecting H0. So there is not sufficient evidence at the 0.05 level of significance to support sigma being less than 0.75.